Welcome to C4.1.1 Group 1, the Alkali Metals. So our learning objectives for today are to recall the physical and chemical properties of Group 1 elements, to predict properties from given trends, and explain the reactions of Group 1 elements. So first of all, we need to know where Group 1 is. So as we should remember from our lessons on the periodic table, the periods are the rows that go across and the groups are the columns that go down. So Group 1 starts on the left-hand side. So Group 1 is the first column on the left-hand side. We're going to ignore hydrogen. If you look on some periodic tables, hydrogen is in Group 1, and sometimes it's not in Group 1. It's kind of floating around the top, not in a group at all. It's put in Group 1 on this periodic table because, like the rest of Group 1, it's got one electron in its outer shell. But because hydrogen behaves differently to the rest of Group 1, we don't talk about it when we're talking about the trends in Group 1. So for the purposes of talking about Group 1, we're talking about lithium, sodium, potassium, rubidium, cesium, and francium. Now, these are called the alkali metals. So they're metals because, as we know, the metals on the left-hand side of the periodic table. So because Group 1's on the left-hand side of the periodic table, these elements are metals. And they're called the alkali metals because when they react with water, which we'll see in the lesson, they create an alkaline solution because they make a metal hydroxide, which is an alkali. So before we look at the alkali metals, we just need to revise our typical metal properties. So we would expect all metals to be shiny. We'd expect them to have high melting and boiling points. The exception that we know about is we know mercury is a liquid at room temperature, so that's an exception. We know that gallium is only just above room temperature. But apart from that, they've generally got high melting and boiling points. We know that metals are malleable, which means they bend without breaking. We know that they're ductile, which means they can be pulled into long thin wires without breaking, and we know that they're good conductors of heat and electricity. So some of these apply to Group 1, and some of them are not typical of Group 1, so we're going to talk about that. So malleable, ductile, good conductors of heat and electricity, Group 1 elements are all of these. So in that respect, they're typical metals. However, the alkali metals are a lot more reactive than other metals. And so they are shiny if they're freshly cut, but they're not shiny if you just get a lump of one and it's had chance to react with the oxygen in air. In that case, you get a layer of oxide around the outside, which is dull. So they don't look shiny. But if you get a scalpel and cut them open, then they look shiny inside until they've had chance to react with the oxygen in air. If you watch the videos that I've put on the link on my website, then you'll see this actually happening. One that's not on there is we'd normally expect metals to be hard, whereas the alkali metals we can cut with scalpels, so they're actually softer than we would expect for metal. They have much lower melting and boiling points that we would expect for typical metal. In fact, we'll look at them as trends later so you can actually see the values, but they're not as high as other metals that we would normally expect. So we're only going to look at lithium, sodium, and potassium because they're the only ones that are safe enough to use in school. The others are expensive and dangerous. All of these, so all Group 1 elements are a lot more reactive than normal metals, and they're so reactive that they react with air and with the water vapor in air. So we have to store them under oil so that they're safe. So lithium, sodium, and potassium all react with water in a similar way. They react with water to make a metal hydroxide, and they also produce hydrogen gas. We should recall from our previous studies that hydrogen gas, we've met in key stage 3, most of us. You can test for that by putting a lit splint in and you'll get a squeaky pop. So if we were doing this as a demonstration and we collected the hydrogen, we could show that it actually was hydrogen. In terms of the metal hydroxide, so if it was sodium reacting with water, it'd make sodium hydroxide. If it was lithium, it would make lithium hydroxide, etc. So all you need to remember is the general equation and just substitute the name of the specific metal into that. For the chemical symbol reaction, it's always the same. The capital N there is to represent the metal. So if we were doing it for lithium, we'd just have 2 Li plus 2 H2O to give 2 LiOH plus H2. If it was sodium, it'd just be 2 Na, etc. So we need to be able to describe the observations with water, so what we would see. So all of them do certain things, but then lithium, sodium, and potassium are slightly different because they get more reactive as you go down the group. So the observations will be slightly different, but all of them are going to float on water. They're all less dense than water, so they will float on the surface. Because it generates hydrogen, we'll see bubbles. But also that hydrogen being produced, because it's produced quite fast, will make it move across the surface of the water. And that will be quicker or slower depending on how reactive it is. So the more reactive it is, the quicker it's going to release hydrogen, the more it's going to move across the surface of the water. In exam questions, they quite often ask you for these observations, and people talk about the water changing colour. We need to be careful that we're talking about adding a universal indicator. So we've looked at universal indicator as a way of measuring pH. So if we put it into water that's come from the tap, we would expect it to be green. It's not always, but it should be. So we'd expect it to be green because it should be neutral. And when we do this reaction, we're creating a metal hydroxide, which is alkaline, so it will normally turn purple. So all lithium, sodium, and potassium all do these. There's just a few differences. So lithium, because it's not as reactive, is only going to move very slowly across the surface of the water because it's not as reactive as the other two. Sodium gives off enough heat that it melts, and so when you see it on the surface of the water, you can see it as a spherical shape. Potassium moves quickly across the surface because it's the most reactive of the three, so it generates more hydrogen quicker, and therefore it moves faster across the surface. It generates so much heat that not only does it melt, but it causes the hydrogen to burst into flames, so you'll see a little flame. And because it's got potassium in there, it will burn with a lilac flame. Sorry, I've misspelt lilac on there. I apologise for that. So we need to be able to explain this trend in reactivity as well as describing it. So they get more reactive as you go down the group. We need to be able to explain why. So we know that when metals react, they lose electrons, so that they've got a full outer shell. So alkali metals are in group 1, so they're all going to lose 1 electron from their outer shell when they react. As you go down the group, so any group, when you go down it, the atom gets bigger, you've got more electrons, having more shells as you go down. So because the atom's getting bigger, the electron that you're trying to lose is further away from the nucleus. And if you think about that electron, it's negative, it's got an attraction to the positive nucleus. If we're trying to remove that electron, then we're trying to overcome that attraction between the positive nucleus and the negative electron. So the further away it is from the nucleus, the easier it is going to be to remove that electron because the attraction is going to be weaker because it's further away. So that's why the reactivity increases as you go down the group. So we need to be able to look at our trend in physical properties. So the density increases as you go down the group. However, potassium's in bold there because it's an anomaly. So the density in there is in grams per centimetres cubed. So you can see apart from potassium, it increases as you go down the group. You should know from physics probably that density of water is 1 gram per centimetres cubed. So lithium, sodium, potassium, as we said, all float on water. If we were to do, and we can't do in a school lab because it's too dangerous, if we were to do rubidium and cesium, then you'd see that they don't float on water because their density is greater than water. So like most metals we'd expect to sink in water, rubidium and cesium will do that. There's some good videos on YouTube of rubidium and cesium. If you look up the periodic table of videos that Nottingham University have done, there's some quite good videos showing their reactivity. So the last trend you need to know about is the melting point. So the melting point decreases as you go down the group. So you can see there it clearly decreases from lithium at 181 to cesium at 29. And as I said before, though normally we'd expect metals to have very high melting points, even lithium at 181 is a lot lower than most normal metals would be. So one of the things we need to be able to do is sometimes, so you're not expected to recall the individual figures for the melting point or density or anything like that. But if you're given a trend like this, you might be expected to predict what the missing one is. So in this case, we're going to look at rubidium and predict what it would be. So if we look at the difference between cesium and potassium, there's a difference of about 30. So if we kind of split the difference and add 15 onto cesium, that would give us about 45. We can see the actual melting point of rubidium is 39, so it's not an exact science, and it's not giving us exactly the right value, but it's roughly in the same ballpark. So hopefully you can do that now. That's the end of the video. Any questions, email me. Thank you for listening.